Hi, my name is Sarah Tang, and my study is about the ground-based follow-up observations of TESS exoplanet candidates. An exoplanet is a planet that orbits a star other than the Sun, and in 2018, the Transiting Exoplanet Survey Satellite, also known as TESS, was launched by NASA to detect exoplanets using the transit method. The general idea of a transit is shown here in Figure 1, along with the corresponding light curve. So we have time on the x-axis and then relative brightness on the y-axis. So notice how during the planetary transit, there's a dip pattern that occurs in the light curve. And this decrease in detected brightness is caused by a planet that is transiting and blocking a portion of the star's disk. And so basically, TESS is able to detect orbiting planets by observing the light emitted from a star over a period of time. In my study, I analyzed pre-calibrated ground-based follow-up data of the TESS exoplanet candidate called LHS 3844b, which I'll be referring to as just LHSb. And I analyzed these data to further confirm, characterize, classify, and analyze the expected spectroscopic properties of the planet. I chose to analyze LHSb because it's considered a target test candidate, and this is because it orbits a red dwarf star, and a study done by Gould et al. In 2013 found that red dwarfs are more likely to host potentially habitable planets. And since TESS is targeting planets similar to LHSb, the results of this study can likely be generalized towards a large portion of the TESS detections. For my study, I developed a pipeline that is modeled off of the pipeline used in TESS to convert the raw starfield images into transit light curve graphs. So the stages of my pipeline are shown here, and they include data acquisition and calibration, photometric analysis or light measurement, light curve modeling, and light curve analysis. For data acquisition and calibration, I remotely obtained images of the star field of LHSb for a single planetary transit of the exoplanet. These data were taken at the El Sos Observatory in Chile on the night of September 6, 2018, and these data were pre-calibrated to increase the signal-to-noise ratio of the data for the greatest amount of accuracy. Then I used a graphical user interface called AstroImageJ to perform aperture photometry, or light measurement within a fixed size, on the target star and neighboring comparison stars. So here in Figure 3 is an example of that process. The target star, which is LHSb's host star, is circled in green, and the neighboring comparison stars are in red. And the light flux measurements of the target star are converted into numerical values of relative flux and normalized with the flux of comparison stars to rid the data of any atmospheric disturbance errors. I used the flux values from AstroImageJ to create the transit light curve graph of LHSb through the Python programming language. So here in Figure 4 is the transit light curve graph of LHSb with hours from mid-transit on the x-axis, and then on the y-axis is flux of the host star, and it's normalized since I fit the baseline to a value of 1 so that I can study the curve in terms of relative flux and transit depth. And the error on the flux are 1 sigma error bars that were generated by AstroImageJ. I used a Python package titled Batman to fit multiple light curve models to my dataset of LHSb. These models were varying based on a given range of values for the radius and time of mid-transit parameters within the Python code. On all other parameters used to create the model light curve were based off of the previously published literature values for the initial test detection of LHSb. Chi-square goodness of fit tests were performed on each data to model pairing to find the best fit model for my light curve. So this here is the chi-squared map that corresponds with that best fit model. So we have hours from mid-transit on the x-axis and then normalized radius on the y-axis. And I use this map to visualize and determine the 1 sigma error bar range, which ends once the color becomes yellow, for my planetary characteristic calculations. Table 1 shows my calculated values for planetary radius and time of mid-transit with 1 sigma error bars, and how they compare to the literature values from the initial test detection of LHSb. So since my light curve plots are in terms of relative flux, I was able to use the transit depth equation, which is shown here in equation 1, to find LHSb's normalized radius, and I found my calculated value to be consistent with the literature measure. However, the mid-transit time I detected for the planet occurred 0.087 hours prior to the expected mid-transit time, which is a significant statistical difference and indicates that the period of this planet can be constrained further with future analysis. This variance in mid-transit time may be the result of an additional planet orbiting the same host star, or it could be due to the lack of repeated observations regarding the transit of LHSb. Along with radius, the mass of a planet is also important in classifying a planet, and since radial velocity measures haven't been taken yet for LHSb, which is typically how the mass of a planet is determined, I thought it'd be interesting to analyze the empirical relationship between the radius and mass of archived exoplanets, and then project the mass of LHSb using that relationship. So here in figure 7, we have radius on the x-axis and mass on the y-axis. So the blue dots represent the archived exoplanets, and then the pink dot is the projected mass of LHSb given my calculated radius value. And the mass of LHSb is projected to be around 3.95, but it's important to note that the projected mass is not constrained very accurately, and a linear regression test revealed that the linear relationship is only 25% matched to the data. But with this preliminary mass projection and my calculated radius value, I classified LHSb as a Terran or Earth-like planet orbiting a red dwarf star. I also wanted to determine if LHSb would or would not likely be considered a qualified candidate for spectroscopic observations with the future James Webb Space Telescope, because currently there are around 4,000 confirmed exoplanets, and it would be unrealistic for the James Webb to observe all of these. And so the James Webb will be specifically looking at emission spectroscopy, which refers to observing the planetary system when a secondary eclipse occurs and the planet goes behind the host star, as shown here in figure 8. And these transits allow us to pinpoint and study the exact emission of the planet itself. To determine LHSb's qualification for the James Webb, I calculated a theoretical emission spectroscopy metric, or ESM, that was developed by Kempton et al. In 2018 that quantifies the expected signal-to-noise ratio of the emission spectroscopy observation of a given planet. And the ESM is shown here in equation 2. So for LHSb, I calculated the ESM value to be 43, and this surpasses the projected threshold of 7.5 for model simulated planets in the literature that were deemed qualified for James Webb follow-up. And so this suggests that LHSb and similar Earth-like planets will likely be qualified candidates for the James Webb, and that's really exciting because studying the atmospheres of Earth-like planets could provide us with more information regarding atmospheric biosignatures. I was also interested in seeing if there's a way we could improve the methodology of the James Webb spectroscopic data analysis, and so I used Planck's law for black bodies for a given wavelength and temperature, which is shown here in equation 3, to plot the theoretical Planck spectra of LHSb and its host star. So the spectra are shown here in figure 9, with wavelength in nanometers on the x-axis and then flux density on the y-axis. And the light blue line is the stellar spectrum of GJ1214, which I plotted as a guideline for the theoretical Planck spectrum of LHSb's host star, since they're the same spectral type and are expected to have similar spectra. And the pink line is the Planck spectrum of LHSb's host star, and the darker blue line is the Planck spectrum of LHSb itself. So notice how the spectra of LHSb and its host star approach each other and are closely matched between the wavelengths of 6,000 and 10,000 nanometers. So I found that this region indicates the observed wavelengths that would produce the most accurate and informational spectroscopic observations regarding the atmosphere of LHSb. And this is because in this range, the signal-to-noise ratio of the planet's emission is greatest because the light emitted from the host star would not overpower the emission from the planet. And these results indicate that the James Webb should analyze spectroscopic data of these target TESS systems of exoplanets orbiting red dwarf stars specifically in the wavelengths between 6,000 and 10,000 nanometers in order to obtain the most accurate information about the atmospheres of these planets. In the recent past, the James Webb launch date has been delayed due to the need for more testing, and the mission is now anticipated to be around $1.6 billion over budget. Around $800 million have been allocated towards operations and data analysis, and my results of the specific wavelength regions we should use to obtain the most accurate spectroscopic data may help us make the data analysis process more efficient, and consequently help reduce the cost of the James Webb, especially since the James Webb will likely be studying many planets similar to LHSb. Additionally, the methods that I used in this study can be applied to future spectroscopic missions other than the James Webb, as well as applied to other host star exoplanet systems, and that's what I'm currently working on by conducting follow-up observations of other TESS-detected exoplanets using the CU Boulder Summers-Bosch Observatory. I'd like to take this time to thank my mentor, William Walks, and my teacher, Dr. Strode, for guiding and supporting me through this project. And thank you for your time.